All right, everyone. We're just about to start. All right, yeah, and this is as close as it gets. Welcome everyone to the first Reddit RPL virtual meetup. I'm glad everyone could make it. And for those who couldn't, this session is being recorded, and I'll share the links with you, everyone. Hey, everyone can hear me, right? I don't think I'm on mute, so I'll assume yes.
Yes, can hear you.
Yeah, I can hear you.
Cool. So we're going to go through two talks today. The first one is by Wouter, who's going to talk about compile time reference counting using lifetime analysis and how it's implemented in the Lobster language. And the second one is by Troels, who's going to talk about Futhark, which is a language for writing data parallel programs. I hope I didn't badly butcher these names. If I did, then my apologies. But yeah, without further delay, I'm gonna hand it over to Wouter. Over to you.
Yeah, I'm here.
Cool.
All right. So let me share my screen. Okay. And everyone see the title of my talk?
Well, I do.
All right. One is enough. All right. Welcome, everyone. So I am going to talk today about compile time reference counting and lifetime analysis Lobster. So this is meant to be an informal talk. I'm not sure how this is going, but if there's something completely unclear, feel free to interrupt or otherwise ask questions after. What am I going to talk about? So first, a little introduction about why we would want any of this, and very briefly what this Lobster language is that we're going to be talking about, and then I'm going to dive into the lifetime analysis that is happening. So first, let's take a step back and talk about memory management. To me, like most of programming language design, it's an example of a design space with no perfect solution. Whatever you do, you're going to make something better, something worse. Depending on the kind of programmer you are, the kind of program you're making, the kind of device you're running on, there's no such thing as the perfect memory management. So there's always trade-offs. The other interesting thing for me is that, choosing your memory management for the language that you're building has huge consequences on everything. Yet somehow, in most languages, this stays fairly hidden to the user. So of course, when we talk about management, the big thing is that nowadays, I would say 90% or more of languages use just one kind of memory management, garbage collection. Of course, there's huge differences between different kinds of garbage collectors, but they are all in the same camp. Me, at least, personally, I feel garbage collection is one of the least elegant algorithms ever made, in the sense that we're not going to try at all from the language of the programmer to understand how our data is structured. And then every couple of seconds or so, we're just going to scan all of memory to try and recover that information. I personally find that a very bad idea, and I would like to find solutions for it. Of course, there are alternatives to garbage collection, but they tend to have limitations. The most famous one, of course, being reference counting, used in some languages. Of course, we know manual memory management. Less known ones like regions, linearity uniqueness types, which have been used in functional languages, and of course this concept of ownership, which we've had in simple forms in language like C++, but recently has gotten more attention because of this little language called Rust. Now, so this is full compile time memory management. with some escape hatches, of course, with all the, you can also do reference counting or cells and things like that in Rust. It is optimal to a certain class of users who likes this kind of thing, but it does have some downsides. It does require you to put like a lot of thought in ownership, borrowing, and sometimes lifetime annotation. That, let's face it, the average GC using programmer isn't going to be doing. We have large amounts of programmers who are currently using GC languages, and for them, Rust is never going to be an option. In fact, we have large amounts of programmers who do not care about type systems. So I think lifetime annotations are a little bit beyond the bulk of programmers, even though it probably would be healthy for them to think more about these things. And of course, there's other downsides. If you go look how people in Rust implement things that naturally have mutable sharing, like tags or other things, then you end up people using indices or arrays, and sometimes even systems that can produce leaks in those arrays. And it is not necessarily entirely without problems. But I think the big takeaway from Rust for me is that it's a fairly almost mainstream language nowadays, and it has shown the world that compile time memory management is a viable thing that we can have. And to me, that's hugely exciting, and that's going to bring on a wave of additional languages that are going to take this further, I think. So to me, the big question is pretty obvious. Is there a simpler form of compile time memory management that we can do? To me, there is a possible design space between Rust and all these GC languages, and there can be things in between there. So can we get most of Rust benefits with some of the simplicity that these GC languages? Well, let's look at a possible picture. I'm trying to see if we can visualize this. So if you look at languages in terms of just two factors, on one axis and the y-axis, we're going to put like how objectively easy it is to program in these languages using memory management. And on the other axis, how much of memory management we do at compile time. And of course, in the one corner, we have languages like JS and Python that are very dynamic and also pretty easy to work with. Then you got your mainstream statically typed GC languages that, of course, are a little bit harder to work with, a little bit more compile time. And all the way in the corner, we got Rust. That can be fully compile time and is definitely the hardest to work with of all these languages. For the fun of it, I put C++ on there, which of course is kind of close to Rust, but does less at compile time in the sense that certain things are not guaranteed in C++. So it fits inside the Pareto frontier of possible languages. Now, of course, to me, it's like there's the question marks on there. Is there a language possible that we could put there that is more compile time, therefore more efficient than those GC languages, but a lot friendlier than Rust? Can we do that? Well, of course, my claim is yes, we can do that. I've implemented something like that, and I want to show you guys that. So I call that compile time reference counting. Before we start, of course, not all of you that are listening are going to know about this language that I've implemented it in. So let me briefly mention what is this Lobster thing that I've implemented this in. So it's mostly my ongoing language that I implement all my fun ideas into, kind of thing. I do not want to go into too much detail here in this talk to let it go on for too long, but it's probably good to understand the rough parameters that we're talking about here, and look in more detail, of course, online what this language is about. If you look at it briefly, it looks almost like it's Python, but it really has very little to do with it beyond the syntax. For example, it's completely statically typed. It does extensive flow-sensitive type inference and specialization. It tries to go very far in terms of giving you a language that feels dynamically typed because you're hardly writing any types, but is still fully statically typed. Then, of course, we have what we're going to talk about today, our compile time reference counting. We also have value types, which is quite important, as we'll see. We put a big emphasis on trying to make higher order functions look like built-in control structures, because I just personally love to wrap everything I do in a higher order function. It's focused on procedural, functional, and object-oriented programming, roughly in that order. I would say it supports all three pretty well, but it's initially aimed at game programming, though it's a general-purpose programming language. I try to focus it on something. So that, for example, has, besides that it's good for procedural programming, it's game. It has built-in vector operations, built-in. In terms of execution nowadays, it runs either with a JIT, or it can optionally be compiled to C++, which. What did we have in terms of memory management before I started implementing the lifetime analysis? Well, that was basically mostly just runtime reference counting. It additionally had leak detection, meaning that if you run a program and you manage to have back pointers or other cycles, then at the end you get this nice error that says like, oh, you had this many objects with this kind of data in it, and those reports would help programmers to insert ways to clear those back pointers manually. So this works pretty well. Personally, quite a fan of reference counting as a. Coming back. Where's the? I guess it's backspace. Oops. Yeah. I'm a big fan of reference counting. It does have fairly high costs because the amount of operations that need to do something with reference counting, increasing, decreasing, or deallocating, is a lot that all needs to be passed through. It's very high cost. The other important thing that we have since before the lifetime analysis is inline structs. I'm a big fan of that too. Of course, the most efficient way to have memory management is to not do memory management at all. And these structs are implemented in such a way they're always copied. They importantly reduce the pressure on lifetime analysis. There's less objects that can potentially have a lifetime that matters, so that's a good thing. Much like in languages like Rust and C++, these things have zero cost, meaning they are completely inline in the parent, and you can put wrap as many structs as you want around a value, and it's going to still have the same cost as if you had that value naked. And I would say, particularly for a language that was initially meant for things like games and computer graphics, where you have lots of 2D, 3D vectors and other things like colors and other things that are just small little structs, it is essential to have this kind of feature. So briefly, also the type system, because that matters for our lifetime analysis. Like I said, it's strongly typed. We do aggressive whole program type inference. Whole program is important because there's certain things we can know about types and about values in our world that we otherwise couldn't. It does automatic specialization. That kind of feels like you have templates or generics pretty much everywhere, or rather, it feels like you're writing in a dynamically typed language where you don't put any types on function arguments if you don't want to, and it automatically just works. It's flow sensitive in the sense that the type checker always knows the current call graph context and can be smart about types, can upgrade types, know that things are not nil in the current context, for example, and such things, so that there's less errors for the programmers and more efficiency for the implementation. It does things like that are possible in language like C++ with if const expr, where basically you can have code that actually has type errors in it, but because the branch is known to be dead, even during type checking, is legal. And that allows some very powerful programming. Okay, so enough of that. Let's get to the actual lifetime analysis. The reason I was talking about type checking just now is because the lifetime analysis is actually deeply integrated with the type checker. Now, I will say that is not necessarily the best choice in the sense that complexity-wise, we take an already complicated algorithm and we make it even more complicated. So that is not great. The type checker is definitely the most complicated part of the Lobster implementation. The problem is, though, that the way the type checker works with specialization and the choices it makes is so deeply interwoven that these specialization choices and how it upgrades types to different types, these choices need to be made together with the lifetime analysis. So to put this in, for example, we'd have to replicate a lot of that information in both those passes. So the lifetime analysis, of course, decides who owns each allocation that gets made, and it assigns either an own or a borrow semantics to each AST node and each variable in a control flow-sensitive way. And this is based on the existing flow-based type checking. The cool thing about this, of course, when you compare this against Rust or anything else that's going on in this space, is that it's fully automatic. So by default, it does not require any program intervention. In fact, in the current version of the language, there is no way to specify anything in terms of whether something borrows, owns, or a lifetime annotation. It does not even exist at the moment. The other cool thing is that I made this rather late in the life of the language. I already have a large body of code, lots of game prototypes and compilers and other things that I have written in this language. And it was my aim to be able to process all that code without having to make too many changes that worked. There were only two places I found in the code where once I added the lifetime analysis that I got errors where I didn't used to get errors before. And those were quite reasonable too. It does not require the program to know that this algorithm exists most of the time. I program in this language all the time, and I really do not get errors because of lifetimes pretty much ever. That's maybe due to me, but I don't know. And I feel because of that, it makes a leap up in that Pareto frontier, the little image I showed you guys earlier, in terms of how easy it is to program in this language. You can mostly work in this language as if it was a GC language, and so how does that work? Is there anything to it? So of course, the only reason that works is that the lifetime analysis tries to do compile time reference counting, but it does provide an escape hatch to runtime reference counting, meaning whenever the analysis fails to know whether something is shared or not, it allows it to happen at runtime. Now that sounds bad. The cool thing is though that in my personal testing with my existing code, that only needed to happen about 3% of the time. So 97% of runtime reference count operations were able to be elided thanks to my analysis. So depending on how fast you want your language to be, of course, people that use Rust might say like even at 3% is unacceptable. But for most users, given that most reference counting overhead would be removed, this is entirely sufficient. And I do plan a future feature where basically you are able to give annotations such that if you do want like Rust-like guarantees on how efficient something is going to be, that you can basically turn this escape hatch into an error. So it will say like you are not allowed to share this value at this location, and then you'll just need to reorganize your code much like you do in Rust. So a little bit about like the lifetime propagation ASTs, like I was just talking about. So basically, for every AST, it has two sides. It has the lifetime that it personally wants to have, and the lifetime it expects from its children, and whatever it passes on to its parents. So there's three possible cases. We have the common case where two sides agree on lifetimes, and that is the completely compiled time case. So for example, by default, if you have something like a constructor or you're constructing a vector, that particular AST node says, I want to be owned with whoever is my parent. And then a variable declaration says, I typically want to own whatever is the right-hand side of this variable declaration. So in this case, they both agree on owning and nothing happens. Then there are cases where they disagree. For example, in this case, the left-hand side by default says, I want to own the right-hand side, and the right-hand side says, by default, variables when they're used, they prefer to be borrowed. So here they disagree. At the moment, this causes a runtime reference count increase in the language. I do have plans that at some point allow new variables to be of the borrowing type as well. A lot more complicated, and so far, at least in my testing, these situations don't occur a lot. So I've left this like this for the moment. Then the opposite can happen. We can have a situation where a child node says, I want to be owned, then we can have a function like print. Print, of course, prints a value, but doesn't want to necessarily hold on to that value after it's done printing. So printing by default says, I want to borrow whatever my argument is. So these two guys do not agree. In this case, what happens, it inserts an anonymous variable. So effectively, this vector will be owned by a variable, but it's not in the source code. And this is very much like what happens with R values in C++. If you insert an R value in C++ in the function call, you get effectively what's an anonymous variable in the current scope. So let's talk a little bit more about L values. Like I said, by default, they own when they get initialized, and they typically want to be borrowed since they're already owned. So how do we accomplish this? So we track all currently active L values. We do compile time reference counting on those L values whenever they get borrowed. Then when such a borrowed value gets consumed, for example, with a function like print, if you pass a variable to print, it gets consumed because it will not be borrowed beyond print. That decreases the the compile time reference count, importantly. And of course, if you try to mutate while an L value still has a reference count, that would be a compile time error. Similarly, if at the end of the scope there is still a reference count outstanding, that is probably actually a compiler error, but that's a different matter. That doesn't currently happen at all. So like I said, in the future, I want to support L values that can borrow their initializer for even less runtime reference counting, but that seems to be diminishing returns at the moment. There's also special purpose optimization for any L value at the end of the scope. Their last use, basically, rather than being borrowed, can be owned because the ownership can be transferred. That is very obvious in the common case of something like returning just a single variable, which we're currently optimizing. It gets more complicated when you have control flow and conditionals involved, and we currently don't do that last use optimization in these more complex cases. But that's, again, another thing that we can do in the future to even further reduce the remaining runtime reference counting.
Is this kind of similar to C++ return value optimization?
Yes, that's very similar. Yeah.
All right.
Yeah, because basically in this case, we prefer that the function, the value that gets returned from a function is, at least in this language, is owned. It's going to be owned by the caller, basically. So,
you kind of like allocate it at the call side stack.
And in this language, no, because we're talking about, in this language, all the values that we're talking about borrowing or owning are heap allocated. All the by value, they get copied. So if you would return something by value, a struct by value, like you can do in C++, in this language that would be fully copied and would not be subject to return value optimization. Oh, this is even simpler in that.
I see.
Okay. So another thing we mentioned is that we actually do function specialization by lifetime. On Lobster, you specialize functions by types, which is not that surprising. But we can actually also specialize by lifetime. Now, why is that important? It could affect efficiency, but it's probably more important in that it increases the amount of code that works error-free, because basically the caller and the callee can agree on lifetimes. And there's no reason that something needs to move between being owned or being borrowed. So here's a very simple example that is probably too simple. So imagine you have this function f. It gets, again, we do not have any annotations to say whether x should be owned or borrowed. So in this case, we're just going to specialize this function. And we're going to say in the first call, we have an argument that wants to transfer ownership to the function. So we specialize it such, and then in this case, we'll have to do that transformation where we have a variable, and we basically, this function will own this value. And in the second case, we actually make a version of this function where f does not own the argument and only borrows it. There are some exceptions to that. For example, if you write this function f and you also then write to the argument, which doesn't really happen a lot in Lobster, but it can happen, that would force it to be owned at the moment. But generally, these functions can be specialized, which again can then make the body of that function specific to either be owned or borrowed, and therefore more efficient. And more importantly, especially once we add the specific error on sharing to be more Rust-like, then that will produce less errors because you can basically have both cases. So how are we doing for time? We're doing pretty good. Okay. So examples of other AST types and how they're handled. We just talked about assignment currently wants to own results in a borrow if you reuse the assignment. Of course, conditionals do a union of both branches. If the branches differ in terms of whether they want to be owned or borrow, it currently defaults to owning. So it will turn the one borrowing branch into owning, which presumably results in a reference count increase at the moment. We have and or that are similar to if, but have special logic for things like A and B or C. So there's in terms of like what values get passed through. So while borrows its condition, we have a special way we deal with string constants. String constants are of course reused a lot. So they're shared a lot, but they're constants. So rather than making those by default would be a lot of borrows that we turn into, there would be like constructing the value by default is owning. So this would be a lot of owning, which we don't want. So instead, we put these in anonymous global variables, and then all these string consts can be borrowed, which is what most of their use cases require. So that reduces the amount of reference counting further. So most operators, of course, only work on value types, the exception being plus on strings, which borrows both of their arguments and results in an own value. There's lots of built-in functions. By default, most of them borrow their arguments and return an own value if it's, of course, allocated. But this can be inverted. For example, there are some cases like the push function, which first argument and the second argument is the element that it wants to put in there. And that, of course, wants to own the second argument because then it doesn't need to transfer ownership further. And the return statement currently always wants to own its argument. And we optimize the single variable case for that. There could be cases in the future where you could return a borrowed value, but again, that gets a lot more complicated in terms of control flow analysis. There are some new errors compared to the case when it's fully runtime reference counting. For example, this is the only error that currently is happening in real code, where you basically have a variable that you initialize to something that is heap allocated. Then you pass that value to a function, and while that function is going on, that function is assigning to the original variable that the current argument is borrowed from. So y is borrowed from x. If we allow an assignment to x, then it would basically delete well, in this case, the string doesn't actually get deleted, but for the example, would delete the value that it owns with a new owned value, and therefore the borrowed value would now be invalid. So this is an example case that we currently disallow. It gets you the error cannot assign to x while borrowed. Surprisingly, this particular situation, like I said, only happened twice in a large body of code. Typically, I'd never run into this error personally. There are other errors that are currently on. I put them in there because they, in theory, can happen, but some of these are, frankly, because I'm not smart enough to guarantee that the compiler is never going to generate them, but I've never seen those in, I've never seen these in practice. So maybe at some point these can be, if someone is smart enough to make a formal proof that my type checker works, then these could be eliminated, but I'm not that smart. So the conclusion to all of this is that we have a very non-intrusive way to do memory management with potentially very close to the efficiency of Rust. So the question to you listeners is this: does this sound optimal to you? We're talking about a Pareto frontier here. So there's many possible designs that lie between Rust and a GC language. It's like, where do you want to be on that frontier? For me, this seems pretty good, but I'm sure other people have other opinions. So I'd love to hear some questions. If you want to read more specifically about the compile time reference counting, there's this URL that explains things in more detail, what I've just been talking about. The general homepage of the languages here. There is a GitHub, and of course, you should all come join the Lobster GitHub for further discussion. Any questions?
Have you seen, or so this is sort of in the same space as the ASAP, as static as possible paper.
Sorry, as what?
What are your thoughts?
So this is in the same space as?
This is in a similar space as the, there's a dissertation, ASAP as static as possible, that does a degree of tracing at compile time and then falls back to some like partial dynamic tracing code. So do you have thoughts on the comparison between that and Lobster?
The term as static as possible does ring a bell. It could be that I've seen the paper, but I do not remember details. It would be hard to say. It sounds like, does that language also basically allow the user to forget about lifetimes if they want to?
Yes, that's I don't know that it's actually implemented for what it's worth, but yes,
as static as possible paper. Let's see if I can find it at some point. Yeah, as static as possible memory management. I found the paper. I don't want to go try and read that right now, but I will definitely have a look.
Could I ask one more question, or does someone else have?
Yeah, that's okay.
So you mentioned a while back in here about like shared mutable state being a problem in Rust. Do you think that's improved by Lobster? Because it seems like if you're using reference counting and barring under the hood, it's not. It doesn't sound to me like that's more safe because you have the problem of reference cycles.
Okay, so one thing I didn't mention in the talk and is important for Rust fans to realize is that Rust is to some extent also as strict as it is because it wants to be able to do shared memory concurrency. So eliminating the possibility of the combination of mutation and sharing is more important because if it would totally break Rust concurrency model if it didn't have that. Now, Lobster currently, its concurrency model is distributed, meaning that there's no sharing of memory whatsoever, and every core runs its own isolated VM memory, basically. So there's no sharing of memory. So, and I believe also in terms of the language, like I said, structs are always copied. So they're never, you cannot, for example, have a reference to a stack location in Lobster. So the implementation is both simpler and it does not have shared memory. So I believe a lot of the things that Rust needs to do are not necessarily hard for Lobster.
Yeah, and I imagine you don't have iterator invalidation like sort of problems as well.
Right. Yeah.
Okay. Thank you.
I wanted to ask a question about the implementation. So you said that this lifetime analysis stuff is being done alongside type checking phase. So do you do it at like the full AST source level, or is it like lowered so that this analysis becomes slightly easier and done on a restricted
it's done on a full AST, which, as you hint at, is probably not ideal. If it could happen at a lower level, it'd probably be simpler because I'm doing this for like a lot of language features that could probably be unified at a lower level. But yes, it does this for the full AST at the moment.
So you mentioned a case where there was basically kind of like a local alias for something else, which would kind of collapse if you would do like an SSA kind of a thing. Is that kind of something like you're planning to do, like moving that?
Well, so yes, like I hinted at in the slide, there are a couple of cases, and certainly the assigning of one variable into another, that I would like to go further in how it currently does. The problem, of course, is for me to move the algorithm to SSA form would be a huge rewrite, because I would first do the type checking, and lower, and retain the. And like I said, there's a problem there because I may want to do things like specialization based on choices I make in terms of lifetimes, which have already happened at that stage. So, okay, so to summarize, yes, there are cases where I would like to do even more permissive lifetimes, but I'm not sure if I'm willing to do that at a different representation level, because that would pretty much mean a rewrite of the entire algorithm and would not allow certain things that I'm currently doing. I think the algorithm can still be pushed further, even in the current. Like I said, for me, we used to have 100% runtime reference counting, and for me, the primary objective was to remove most of that, and that objective has been reached. So I think further lifetime improvements are more important, not for efficiency, but for allowing programmer control. At some point, we'll have annotations for programmer annotations and all this stuff. And then, of course, the problem becomes trying to reduce the amount of cases where this produces an error for the programmer. But I haven't really gotten into that yet, because it works so well at the moment. That time for that I'm doing at the moment.
Yeah, that kind of answers the question.
I have one if we have time.
Sure, go ahead.
I was just wondering about the lifetimes. Do you just keep track of lifetimes, or is there more to it? Okay, actually, I should clarify. I noticed when I was implementing my language that you don't actually want to just keep track of the lifetime. You want to keep track of when the object should be constructed separate from when it should be memory allocated. And I was wondering if you found that situation to be true for you, or like how did that go?
So at least in my case, there is no construction and memory allocation happen atomically, or at least they're not observable to be different in this language. So this is not particularly, that's the thing, compared to say C++ and Rust, this is a fairly high level language, though it can be, the way it's doing lifetime analysis and the way we have value types nowadays, it can move to be a much more lower level language as well, but it originally is designed as a very low language. So there's no concept of allocating memory separately from constructing it.
Okay, thanks. I was also wondering about the compile time, like if you found it to be fairly fast or fairly slow, but not important.
So there is not a lot in the lifetime analysis, not just that's not fairly linear, just the size of the code that is processing. So I've done tests at some point. Compiler is not crazy fast. There's some people that can basically compile as fast as they can put from disk. This is slightly slower than that, but it's certainly compared to, I'm used to writing in C++. This is probably 100 times faster.
That's pretty.
There's no problem. There's other languages that are faster yet, but this is I've never had any. There's no O n squared algorithms or anything like that. part of the lifetime we're checking. It does, of course, specialization does blow your code up times.
So
It is a cost. That happens in Rust and C++ also. Not necessarily. Yes.
Yeah, you mentioned the code bloat thing. So is it like every argument can like potentially be polymorphic in like two different things? Like for example, a function that takes a single argument, you could potentially have specialized versions of that function which either borrows or either owns. Is that correct?
Yeah. So in theory, this could explode spectacularly in the sense that like each argument can have a different type and a different lifetime, and you can get all possible combinations of these things. In practice, in most programs, you'll find that most functions are called, or most arguments tend to have the same lifetimes, and the amount of different types is not that great either. So I have not observed any really bad cases myself. Of course, here specialization is, I guess, even more aggressive than it happens in Rust and C++, because in Rust and C++ it's fully under programmer control. Here, it might occasionally happen, even if the programmer didn't necessarily even care to have specialization. That's the thing. I am, like I said, I'm keeping an eye on that, but so far, I've seen in my testing so far that most programs blow up by about 2x compared to the parsed AST. Sounds like a lot. To me, it's entirely acceptable on most machines nowadays. So. I guess it's an interesting topic, specialization. I work with a lot of people in terms of doing compiler stuff, and there's some people out there that feel specialization is the most evil thing because it blows up code. I think it's the most wonderful thing because it allows us to specialize everything and be super efficient. So, you know, your mileage may vary. I really like it.
I'm gonna give more seconds for any other questions. Otherwise, we can probably move on to Troel's talk. So,
yes, shall I just take over the screen share?
Yeah, sure. Go ahead.
Okay. Is my title slide visible, and can you hear me?
Yes.
Good. Okay, so I'm going to talk about the design and a little bit the implementation of the programming language Futhark that I'm working on and have been working on for a few years as part of my my research as a researcher at the University of Copenhagen. So most people are in a hurry and we want our programs to run fast, and people keep coming up with new kinds of programs that need to run fast and really push the capacity of our computers. Unfortunately, modern parallel machines like GPUs or even more exotic things like Google's TPUs are pretty difficult to program. And unfortunately, due to physical limitations, we're not likely to get machines that are faster without also making them more difficult to program, because we need to make them more specialized, because we can't just keep cranking up the frequency. We haven't been able to for over a decade now. And that's a problem, because humans are not very good at reasoning about the kinds of massive concurrency that modern machines need in order to reach their peak performance. And I don't mean to insult humans. I'm a human myself, but our brains, the hardware between our ears, evolved for chasing down gazelles in the savannas of Africa. And our brains haven't really changed all that much since then. They certainly haven't evolved to do massively parallel computing. So it's very hard for humans to kind of keep track and reason intuitively about what's happening when tens of thousands of threads are all trying to work on the same piece of data at the same time. So we need some kind of discipline. We need a sequential programming model that allows us to reason in terms of one thing happening after another, because that's apparently how our brains work. So Can we just do nothing and assume that someone will write a sufficiently smart compiler that will make all of our old C code and all our old Fortran code run in parallel on our new fancy machines? Well, probably not, unfortunately. So let's take a look at this loop written in an unnamed legacy language. It is by the immediate language semantics sequential, because it's a for loop, so it just starts at I equal to 0 and then up to n. So is this a parallel loop? Well, probably, or yes, depending on some details. But a compiler would have to look at the indexes and realize that the different iterations are actually independent in order to see that this could be that all of the iterations here could be executed by a separate thread or whatnot. Oh, and if you have any questions or objections, don't hesitate to interrupt me. It's possible I'm wrong about everything. But there do exist compilers that can analyze this and parallelize it. So what about this one then? So this is a more complicated loop. It turns out this is actually also parallel, but it's not embarrassingly or naively parallel like the other loop. And I don't think that any compiler, not even cutting-edge parallelizing compilers, can actually detect that this is parallel. So what I think is tragic here is not just that compilers have limitations. Compilers will always have limitations, but the real tragedy is that very often when we think about our algorithms, when we write them down on paper, on our whiteboards, we do write them down in a way that is parallel, because like when you write down a matrix operation, that is inherently parallel. There's no dependencies between the different elements of the matrix, but then you write it down in C or some other common language, and you are forced to decide on an iteration order in your loops, which forces a sequential ordering that didn't exist in the algorithm, that didn't exist in your head. But the nature of the language forced you to come up with an ordering that is artificial, and then now you expect the compiler to be able to reverse engineer what you wrote and figure out what you actually meant. And to me, that's not productive, and it's kind of the wrong way to go about things. So I think that if you want to program these increasingly massively parallel machines, we need to improve our programming vocabulary and stop artificially enforcing dependencies that don't actually exist. So for example, instead of writing that for loop there, I would say that we should write as a map instead, where we just say apply the function map to each element of the collection XS, producing a new collection YS. That makes it clear to the compiler that there are no dependencies between the different elements of YS. They can all be computed in parallel if that's advantageous. Maybe it's better to do it sequentially, who knows? But now the compiler has freedom to decide without first having to spend a lot of time figuring out whether it would even be safe to do so. Similarly, the second loop corresponds to a programming language pattern called a scan, which is also known to have efficient parallel implementations. And what's particularly nice is that these things, map and scan, they're not just terms that I invented. They are actually well-established terms in the functional programming community, because functional programming, while it's not always, or while it's maybe even rarely actually run in parallel on real machines, the vocabulary that functional programming employs, this notion of doing bulk operations on data with high or higher order functions, is actually a pretty good vocabulary in most cases for doing parallel programming. That gives the compiler a lot of freedom in generating code. So I think that functional array programming is a programming model that is in principle parallel. It's rarely actually turned into parallel code in practice, but in principle it could be. And the real trick, or in my case, the research question, is then how we take this kind of functional code and then generate low-level code for real machines that's also in practice fast, because that is ultimately the point of parallelism. Right now here, I'm not trying to say that you should do functional programming because it looks nice or it's more correct. I'm doing this for performance. So in particular, because we are a small research team, we didn't try to create the next big general purpose language that is going to take over the world. Instead, we have designed a very restricted functional language that only contains the features that we know how to implement efficiently. So it leaves out a lot of stuff that is nice to have, but we just don't know how to run fast. But it's of course still flexible enough to write the programs that we care about, which are computational kernels, not general purpose programming. And that language is what we call Futhark. It's a functional language in the ML family with a syntax that looks like a mixture of Haskell and standard ML. And I think it's okay to programming. It's nice, but the point of it is practical performance, not just niceness. And it does have some limitations that are not nice, and only a few features that are not present in existing functional languages. So apart from the language, which is what I'll spend most of the day talking about, it also has a compiler, which is why we actually spend most of our time developing these compiler optimizations. And there's a whole battery of optimizations, far more than I'm going to talk about today. And ultimately, at the end, the compiler generates either multi-core code via the POSIX threads or GPU optimized code via the OpenShell or CUDA low-level APIs. So let me go through some small examples of Futhark programming. So what you see now, I hope, is a REPL for Futhark. So we can define a small array and another small array. Let's give it some different values. And we can ask for the type of an array. And already here we see a slightly unusual feature of Futhark. So this is the type of an array of 32-bit integers of size 4. So Futhark tracks the sizes of various things in the type system. That's one of the few novel things in Futhark that you won't find in most common functional languages. And that's useful because the array is the main composite data structure in Futhark. It's an array programming language. So when here we have A and B, then we can do things like zip them together, so we get an array of pairs. And here Futhark will suffix each value with its type. That's nothing. That's a little bit verbose, but that's just how it is. And we can apply data parallel operations like map. So we can say map +2 over A, and it'll give us back So this is the interpreter. So this is all executed sequentially. But if I execute this in parallel, if I compile this with the optimized compiler and run it on my GPU, I would get the exact same result, and I wouldn't have to even worry about race continuity or anything like that, because the semantics of the language are completely sequential. There's no room for anything to be non-deterministic, except for a few dark and dusty corners that I won't be getting into. So we have map as one example of a data parallel operation that maybe we will run in parallel. That's up to the compiler. Another is reduce, which we can use for compressing or reducing an array to a single value with a given operator and with a given neutral element. So if we say reduce the array A using plus as the operator and 0 as the neutral element, then we get the sum of the array A. Now, what we have now is basically enough for us to start writing a useful Futhark function. Like we can write a function for computing dot products. And let's say dot product takes two arguments, x's and y's, the two vectors. And then we use the map2 function for together adding the element-wise the two vectors here. So as an example, I can just show you what it does down here. It's A and B. Yeah, it just takes element-wise the first element of A and adds it to the first element of B and returns that, and so on. So it's like a combination. This is what would be called the zip width in Haskell. So using that, we can add together the two vectors we are given, and then we can sum them together, the result, and then we have a dot product, and we get a warning from the compiler saying that we didn't put any type annotations on it, so it assumes that the elements of the vectors are going to be integers. That's what it assumes for integral types or for numeric types. And now we can call dot product on our A and B, and it'll we have to actually redefine it. The interpreter removes any local definitions when you load a file. Unfortunately, I forgot about that. So now we can run dot product on A and B, and we get back the dot product. If we ask for the type of dot product, we can see that it takes as arguments two functions, xs and ys, and those two arguments here must have the same size, some n0, that is a size parameter to the dot product. We don't provide this size parameter explicitly when we call the dot product function. It's passed implicitly, and we must provide it two arrays of the same size. So if we call it with two arrays that do not have the same size, then we would get an error. So the Futhark language has a small size-dependent type system to catch these cases. Okay, but mostly Futhark really is just an ordinary functional language, and it it will look familiar to most people who are familiar with an ML or Haskell dialect language. We're really not trying to innovate much in the language design. That's intentional. We want to innovate in the compiler instead, because functional programming, once you remove a few things that are very difficult to implement efficiently, is actually a really good parallel programming model. It's not perfect, but it's pretty good. So I have some examples in case my interpreter didn't work. So let me just re-emphasize what the goals of Futhark is. In one sentence, our goal is to be faster than everything that is more flexible, and more flexible than everything that is faster. So there will be languages that are faster, but then we think that they are more difficult to work with and cannot express as many programs. And there are many languages, of course, that are easier to work in, that have more features, but then they won't be faster. They will be a lot slower, probably. We are in particular not interested in taking over the world, because that's kind of a hassle, and we like small languages that do one thing well, and we are going to leave the whole problem of doing a lot of things kind of mediocre to other languages. Like, I like Haskell. That's what the Futhark compiler is written in. So we don't really want to replace all languages. Futhark doesn't want to kill its competitors, because it sees them as colleagues, not competitors. Futhark is really kind of supposed to be used for what Fortran is used for, just writing these small performance-sensitive computational kernels, which are then called by programs that are mostly written in other languages. So we just want to replace a few of the inner loops, the ones that take up most of the time. Okay, so now I'm going to talk a little bit about the implementation. Since Futhark has very few features, but it does, you would think that the implementation might be simple, but unfortunately, performance is a feature that kind of tends to make every other feature in a language much more difficult to implement. So even simple things become tricky when you really want to run fast. Like, one thing that's problematic is high order functions, and that kind of sucks because it's hard to have a functional language without high order functions. And normally you implement these as function pointers, and if you want closures, you then have a pair of a function pointer and an environment pointer. Unfortunately, many high-performance machines like GPUs do not efficiently support this kind of ad hoc use of function pointers. And indirect calls, like when you do an actual function call through a function pointer, are relatively slow, even on CPUs, and they are barriers to optimization because you have no idea what's on the other side of that function pointer. Fortunately, the 70s was full of people who also did not like function pointers. So we looked at some old ideas for how to handle high-order functions without actually using runtime indirection. In particular, we looked at the defunctionalization by John Reynolds, who came up with the technique in 1972, not because he was using machines that didn't support function pointers. I don't know if he was, but I don't think Reynolds actually ran most of his code. But he was using some formal analysis methods that could not handle high-order programs. So we wanted to be able to turn high-order programs into first-order programs. And the basic idea is to turn every lambda abstraction written here in Haskell syntax. So the backslash here is a lambda of one parameter, and this is the body. So it's an anonymous function here. Instead of producing a lambda, you produce a constructor in a sum type, so some kind of record that encapsulates the free variables of the lambda, so the y here. And in this lambda here, the y free variable is set, so that's what you capture. And then you distinguish with some kind of tag every lambda in the original higher order program. And then whenever you have a function call, you then replace that function call with a big case statement that cases over every possible function that this could be, and each function is represented by one of these lambda constructors. And then based on what function you find, you do you run the body of the function. So this replaces function pointers with a big branch that just checks every possible thing that function pointer could point to. So okay, yeah, it's technically first order now, but those branches are really not great. I mean, branches are also problematic, both on CPU and GPU, and they are also optimization hindrances. So what we did was come up with a bunch of type restrictions in our type system to ensure that we always know when you call a function exactly which one it is that is being called. So here's an example of when we wouldn't know, where we have some kind of conditional here, if that produces various functions, and then we are binding the result of that if expression to a value f, and we are calling f. So at compile time, we have no idea which of these functions are actually being called when we call f. because that depends on which way these branches go. So in our type system, we have some type rules that ban conditionals like if or pattern matching from returning functions. So that solves that. Similarly,
So,
yeah.
Can I ask questions in the middle,
Sure.
or should I wait for the end?
No, just ask now.
So is this kind of like you're inlining all the closures?
Yes, we'll get to that. That is exactly what we're doing. That's a few slides ahead.
All right, cool.
Okay, so another case where we ban functions are as array elements, because if you have an array of functions and you're indexing that array with some value I, then you have no idea statically which of these functions you're going to find on the other side of that index. So we also ban arrays from containing functions. And the end result of that is that whenever we have a function call, we can do a kind of partial evaluation to insert exactly the function body, or insert a call to a function that contains exactly the function body, even if it's a function that has been returned by some other construct. So as a very simple example, let's look at this function f that is produced from a lambda literal here, and that is being called down here. So that's very simple because it's used immediately, but it could have been more complicated also. So defunctionalization replaces the lambda literal here with a record that contains exactly the three variables. So Futhark supports anonymous, also called structural records. So this creates a record with a field called a, whose value is in the value of the variable a, so this one here. And then we replace any call to the function f here with a call to the lifted function that is then being called with the f, the record here, which is really the closure of the function. This is the environment, the three variables. And then also the b, which is the actual argument that the original function call contained. And then the lifted function here, the f prime, just takes the environment, extracts the three variables, and then inserts the original function body here. So then you end up with a completely branch-free first-order program, as long as the original program satisfies certain type constraints, which are mostly don't turn functions from branches and don't put branches in arrays. And so that's a restriction. Haskell doesn't have that limitation. So this is one example where Futhark is less convenient in order to get more performance. But in practice, it turns out this is not that problematic for the kinds of programs you want to write. This didn't really crop up in practice, and it very, very rarely crops up when you write new Futhark code. And the restrictions are pretty easy to explain to programmers. It's not a very exotic restriction. It's not something that shows up after the compiler has rewritten your program and it finds out that it can't. This is just a top-level type restriction that is pretty easy to grasp for a programmer. Now, so let me talk a little bit about value representation also. So Futhark is pretty simple. It unboxes everything, and everything is called by value except arrays, which are passed as pointers. In particular, that means that if you have a triple, ABC, then that's treated by the compiler internally as three distinct values and probably kept in registers. So they're not heap allocated or anything like that, which simplifies many things. It also has the main downside that if you call a function with an enormous record, then that's actually going to be copied to the function. But that hasn't really turned out to be much of a problem in practice. And it creates a fairly simple program model. You get exactly what you ask when you write Futhark. You write a tuple with two values, you get two values, and that's it. So one place where we're a little bit more tricky are when you have arrays of complex types, in particular tuples. So consider having an array of pairs where each pair consists of a 32-bit integer and an 8-bit integer. So since an I32, that's the 32-bit integer, is 4 bytes, and the I8 is 1 byte, how should we actually represent such an array in memory? Well, one option is to do it like this, where first you just have the elements consecutively. First you have the 4 bytes of the integer, then the 1 byte of the I8, and then another 4 bytes for the next I32, and so on. So that's obviously optimal in terms of memory use. Unfortunately, it results in unaligned access, because now this I32 here, it starts at an offset of 5 bytes within the array. And unaligned accesses are, on some machines, they are slow. On some machines, they are forbidden. And even on machines where they're normally allowed, such as on Intel x86, they are often not allowed when you do things like using vector instructions, which we really want to do when targeting CPUs. And on GPUs, they're typically these unaligned accesses are typically not allowed at all. And on GPUs, you also have other problems with the memory access not being coalesced if you have neighboring threads that want to access these two I32s in the same clocks. So this is not a very nice format. Another way of representing it would be to pad every I8 to take up 4 bytes. Then you definitely have aligned access. Now everything is located at an address that is divisible by 4, so we have nice alignment. The problem is that we're wasting memory, because now, even though we really only need 1 byte for each of these, we're using 4, and that means that the element that the array element that should take up 5 bytes now instead takes up 8. So that's almost a factor of 2 overhead. So that's not really ideal, especially not on machines like GPUs, which don't have too much memory in the first place. So what we do, and this is a pretty standard technique, but it's a little bit unusual for compilers to do it automatically, is that we rewrite arrays of tuples, such that instead of having a tuple of instead of having an array of tuples, you have a tuple of arrays, so you have multiple arrays. So in this case here, and one array that contains T1s, T2s, and T3s, we have 3 completely separate arrays that each contain T1s, or T2s, and T3s. So in our example before, when we had the array of pairs, now we have an array solely for containing the I32s, and a separate array just for containing the I8s. So now all of the I32s are perfectly aligned, and all of the I8s take only 1 byte each. So this is an optimization that high-performance programmers usually do by hand, and it's crucial. It's a really, really important optimization, and it's typically called the struct of arrays transformation in legacy languages. The Futhark compiler automatically does this behind the scenes, always, without that being visible at the surface language layer. So you don't have to know that this happens. And it's kind of important because it also matters, or it also kicks in whenever you have arrays of records, or arrays of sum types, or arrays of anything that is not a primitive. Then you need to do this kind of transfer. And it only affects the internal language, so it's just a runtime representation thing without any visible impact on the semantics. So that's a pretty big success.
Is there a way to control this, because this kind of a transformation potentially might have locality impact?
Yes, so there are some cases where this is not optimal, or where it's at least not needed. In Futhark, the programmer cannot control this. It's always done. And it seems that for the kind of bulk data parallelism that Futhark is built for, the cases where this is not optimal are pretty rare. But in principle, there will be some cases where this is not the right thing to do. We just haven't encountered them in practice yet, so we haven't worried. And we do have we have a lot of Futhark programs by now, so it's not going to crop up very often, at least. Okay, so that was more or less what I had to say today. So I can talk more about the language and the implementation and all that, but I think actually one of the main takeaways that I have from my work on Futhark is that it's really, really fun to work on a very small and focused language, because realistically, if you're trying to write a general purpose language, you're probably not going to be better at most things than the existing general purpose languages, because they've had armies working on them, and writing a language that is good for everything is extremely hard, and it's not necessarily even a well-posed problem. But if you write a very small and focused language, really just a spear point that tries to solve one thing really well, then there is actually a pretty good chance that you will write a language that is better in one particular area than anything else that exists. And that's extremely satisfying. Maybe a very small area, but psychologically, it really feels great to know that your language is the best at one very small thing, or at least that it's one of the best. The second thing is that if performance is a feature that you really care about in your language, then you need to think very hard about what the language permits, because every feature becomes much more difficult to implement when it has to run fast, especially because language features that in isolation look pretty easy to implement efficiently may become tricky once you combine them, and it can be hard to predict when that will happen. I have written lots more about our approach to language design and our experiences, and I have some links to the blog post, which are probably not particularly readable here because that's the lines are broken. But in particular, the first one here are my memoirs on when I was a PhD student, and I was supposed to do research on compiler implementations, and I ended up doing language design instead. It's both about how language design can be fun, but also when it can be particularly frustrating. And then I also have another blog post on how I think that you should design programming languages that are realistically not going to have very many users, and where you're also not realistically going to design advanced tools. So it's basically about how to get the most bang for the buck when doing language and tool design. Okay, that was all that I had to present to you today.
Could you talk a bit about the memory management model for Futhark?
Yes, it's very simple. So Futhark is it's an array language, and it does not support any kind of references or pointers or anything like that. So it is guaranteed that there cannot be reference cycles. So it just does reference counting, and because it reference counts at the level of arrays, the number of objects in a program is usually fairly small because that's the number of arrays you have, not the number of array elements. So it's pretty rare that it actually has to adjust the reference counts compared to the program runtime. So it has absolutely no performance impact. So reference counting is a fit for a bulk data parallel language.
Makes sense. I guess it probably answers this other question. Have you considered adding some type constructor for boxing, putting something onto the heap, since you mentioned that potential case of passing a very big value?
Yes, so that's a workaround of just making a single element array and passing that around, if that's what you want.
Oh, I suppose it's your static lengths.
So sorry, what?
I guess that's true because you have static lengths.
Yes, yeah, so you could just do that. But more generally, heap allocation and boxing would be useful, but it's extremely difficult to implement because what happens when you have some code deep in the innermost loop on a GPU, or even just on a GPU at all, and you need to allocate some memory? I mean, and that's just one thread out of 100,000 that needs to allocate memory. How do you synchronize that? What if 50,000 threads all need to allocate some memory at the same time? It's really hard to do this efficiently. It's not impossible. It may even be impossible. It's possible to do it correctly. I have not seen it done efficiently by anyone. So,
Thank you.
Hello. Could you speak a little bit to if any decisions are made about what to run on a GPU versus a CPU? For example, if there's a small operation, would that be run on a CPU to avoid the memory transfer to a GPU?
no, right now we have a fairly simple compilation model. If you use the GPU compiler backend, then all arrays will always be stored on the GPU, and all bulk parallel operations will be parallelized. And if that's not what you need, then you can use our multi-core CPU backend. But this is something that we probably need to look at, because in most programs there will be some things that are not worth putting on a GPU, maybe in some initialization stuff or a little bit of bookkeeping, but right now it will be run on the GPU, and it's probably wasteful. But this is again one of these things that we thought we would have to address fairly early on, but then it just never really seemed to be a problem in practice, even with dozens of programs and benchmarks written. But probably someday, because it is a problem. It is a potential problem.
Okay, thank you.
All right. I think thanks a lot for that, Troels. That was a really great presentation. Appreciate it. I think that's pretty much it what we had for today. And again, thank you to Wouter as well for giving your presentation. Really appreciate it. That was great. and it was amazing that all these people could attend, and yeah, I think next time it will be a little bit more professionally done. Thank you for everyone for helping me out. I'll post the videos, video links online, and yeah, look forward to that. Uh, does anyone else have anything else to share? Otherwise, we can probably drop off.
I would actually caution against making it too professional. I think there's value in making people feel welcome, because it is just a bunch of people with shared interests who meet up to talk about their nerdy hobbies, and people shouldn't be discouraged from presenting because they don't have a polished presentation, or they don't have whatever. They don't feel that they have something that's sufficiently advanced or nice. I mean, that's why I did an ASCII art presentation because this isn't an academic meetup. This is just a bunch of people who like programming languages, and I think we should try to keep that spirit.
That makes sense, and yeah, I did cut my bit in the interest of time, but I'll present it next time. So thanks for that. But yeah, I think this will be all for today. And again, thank you to the presenters. I appreciate it a lot, and I'm sure everyone who attended did so. So till next time, bye everyone.
Thank you.